So let's talk a little bit about solutions. And when I talk about solutions in the context of heterogeneous solutions, certainly one of the first things we need to understand is there's two components to a solution. There's the solvent and there is the solute. Now, the solute can be a solid, it can be a liquid, or it can be a gas. And of course, the solvent can be a solid, or it can be a liquid, or it can be a gas. Typically, with the kinds of questions that you will have to deal with on the DAT or the PCAT, the solvent will typically be water. Not necessarily, but typically it will be water, while the solute will either be a solid or it will be a gas. So let's discuss the solubility of a solid in water. Specifically, we want to talk about how does the solubility of a solid change when I increase or decrease temperature, and when I increase or decrease pressure. And the short line answer for this is it depends upon the nature of the dissolution process. So in order to really discuss this with all the detail that we need to worry about on the test, let's talk about the process of dissolution. So in the process of dissolution, it is thought to be a three-step process. So before dissolving, you have solvent molecules that have intermolecular forces one with another. So again, if we go back to water, you're talking about hydrogen bonding, intermolecular forces that take place between water molecules. And just to address this in a little bit more depth, you have a central oxygen atom, and you have two hydrogen atoms. Of course, this is a bent molecule that's part of the tetrahedral family. And of course, there are two lone pairs around the carbon. Now, oxygen is more electronegative than hydrogen by a pretty good margin. So this oxygen has a partial negative charge, while each of the hydrogens have partial positive charges. So electrostatically, these hydrogen atoms are fairly significantly stripped of electron density. And so if we have a second water molecule, and the thing to remember here is that oxygen's pretty small, so it can get to about within 2 angstroms of this partial positive charge. And of course, it's partially negatively charged. So this electrostatic interaction between the partially positively charged hydrogen of one molecule and the partially negatively charged oxygen of yet another water molecule, you have a hydrogen bond. if we're going to dissolve a solid in water, the first step is we must break the IMF between solvent molecules. This is intrinsically an endothermic process. It requires energy to break a favorable electrostatic association. So we've learned previously in thermodynamics that bond breaking is an endothermic process. You may regard breaking an IMF as kind of sort of breaking a bond, simply not as strong. So it's going to require energy. That's step one. Step two deals with the solute. So let's imagine we have NaCl. Now you need to remember that the cation is smaller than the anion. So in a lattice, you're going to have a three-dimensional arrangement in which you have a cation next to an anion, next to a cation, next to an anion. So if I have a cation, I'll have an anion above and below, to the right, to the left, in front, and in back. So I have this three-dimensional array. So if we look at one layer, if you will, then I would take a second layer, which is complementary to this layer, like so. And I would stack the layer that I'm drawing on the bottom with the layer that I've already drawn on the top. And that's what a lattice looks like. So you have to use a little bit of creativity to see this lattice develop. And this lattice is just a conglomeration of ions. And before we can dissolve a solid into a liquid, we have to also break these ionic bonds between each Na plus and each Cl minus. So the second step, we must break the IMF between solute. I'm not going to use the word molecule because this really isn't a molecule, but I will use the word particle. The word that is most appropriate here is a formula unit. This is also an endothermic process. The third step is that I will form IMF between solute and solvent. This is necessarily exothermic. Now, the solvation process will either be exothermic overall, or it will be slightly endothermic, but it will produce a greater entropy than we had with the sum of the solvent molecules bonded to each other and the solute molecules or particles bonded to each other. Most solids, when I dissolve them in water, will dissolve in an endothermic process. So what that means is NaCl, which by the way is only very slightly endothermic, will absorb heat from the surroundings. And of course, there's going to be an equilibrium constant, K, and I will solvate aqueous sodium ion and aqueous chloride ion. And of course, water is going to be the minor constituent of all this. So remember that a solute is the minority component of the solution, whereas the solvent is the majority component of the solution. If I increase temperature, I necessarily, in an endothermic reaction, increase the concentration of heat. To offset the stress, Le Chatelier's principle states that there will be a shift to the right, which means more solid dissolves. So from this, we can derive the following statement. Typically, there are lots of exceptions to this. Increasing the temperature results in increased dissolution. Doesn't say anything about the speed, but I'll get more solute dissolved. If I wanted NaCl to be more completely dissolved, I would simply heat the solution as I'm dissolving. But as I said, there are exceptions to this, and one of the most notorious exceptions to this is NaOH. NaOH is very highly exothermic. So let's say I had some NaOH pellets, and I wish to make a solution. Now I'm not indicating this in the detail that I should, but Na plus and OH minus are completely solvated. And since it's an exothermic process, heat is a product. If I were to heat up this solution, less would dissolve because I would increase the concentration of heat, and then Le Chatelier's principle would predict that I would have a shift to the left. So as a point of practicality, if you're trying to make a solution of NaOH in the lab, you let it cool on ice and you get a more complete dissolution process. So point number one, when we're talking of dissolving a solid in a liquid, increasing temperature typically, not always, but typically results in increased dissolution. The second set of conditions is when we increase pressure. Let's remember that solids are relatively incompressible. Since the pressure is not really going to do much in terms of minimizing surface area or increasing the amount of compression, increasing the pressure or decreasing the pressure for that matter has no effect on the dissolution of a solid in water. So either increasing pressure or for that matter decreasing pressure will positively or negatively affect solubility. So it has no effect So if I increase or decrease pressure, we've already seen that temperature, increasing it will usually increase solubility of a solid in a liquid. Decreasing it would have the opposite effect. Increasing or decreasing pressure has no net effect. on the solubility of a solid in a liquid. So pressure has an effect, but pressure does not have an effect, temperature does have an effect.